Stay with me. I need this. So this is A and this is B. This is the first interval, the second, the third. What is the width of the first subinterval? What is the width of the second subinterval? What is the width of the next subinterval? Of course, we got the idea. And so on and so forth. So this is the initial value, which is A. Can anyone give us the value of the end of the first subinterval, which we will call x1? Yes, Andre? A plus 1. 1 what? Of course, delta x. Very good. Now I would like to determine the end of the next subinterval. Can anyone give us x sub 2? Excellent. Can anyone give us x sub 3? Of course, I want the xi. Why do I want xi? For this. Because I want to use the summation notation. So I want xi. Can anyone tell us what does xi equal to? A. Of course. And I can continue forever. Okay. So then xi. But you could say, wait a minute. You're using the rightmost point. But what if I want to use the leftmost point? What if I want to use the midpoint? It doesn't matter. We're going to make n approaches infinity. Who cares? It can be this, it can be this, it can be this, it can be this, it can be anything within that delta x. Who cares? N goes to infinity. It would be like this. It doesn't matter. So don't get, worried about that. It doesn't matter because we're going to make n approaches infinity in a minute. Okay, so then xi we know is the leftmost point of the interval plus I delta x. Perfect. So now for any function, this is our function, this is the interval a comma b. We want to find the exact area under the graph of f of x between a and b. We will have a sum of areas. Delta x is the base. What is the height? Base times height plus base times height plus base times height. What is the height for each subinterval? What is the height? F of xi. For each x, it changes. The height changes, right? So for the first subinterval is this height. For the next one, it may be this. For the next one, it may be this. For the next one, it may be this, right? So it's for each subinterval. From I equals 1 through n subintervals, I have to multiply by f of xi. We're not done. Let's discuss this one more time. So in order to find the exact area, I have to add the areas of all these subintervals, rectangles, right? Okay. So I add the first, to the second, to the last. Perfect. So I have the sum of all of them. But now what am I missing in front? I'm missing what? Careful. So here I'm adding the area of the first, to the second, to the third, to the fourth, to the nth one. But I don't want to stop at n. I don't want n to be 16. I don't want n to be 35, 32. I don't want n to be 128. Ready? Of course. I need the limit. When n approaches, what does it approach? Infinity. I don't want to stop at 4. I don't want to stop at 8. I don't want to stop at 16, not at 32, not at 128, never. To make sure that this is the exact area, I have to make n, the number of subintervals, go to infinity. This has a name. This is called the Riemann sum. And we say that the exact area under a graph of a function on the interval a comma b equals the limit of the Riemann sum. Not just the Riemann sum. It has to be the limit. Because we don't want to stop at n. Whatever n is, I want n to go to infinity. And now it's guaranteed to be equal, be exact, not approximation. Do you remember when we started this course, we had to determine the derivative using the definition of the derivative, and then we learned differentiation rules? Same idea here. First, we discuss the limit of the Riemann sum, and then we will go to the next level. However, we are limited when it comes to the limit of the Riemann sum to only linear, quadratic, and cubic functions. We cannot determine the limit of the Riemann sum for anything else. We do not have the backup. We don't have the calculation. We don't have a way of determining by hand the limit of the Riemann sum for any function other than linear, quadratic, or cubic. We're going to look at an example right this moment, but we need 4 identities. 4 identities, without which we will not be able to determine the limit of the Riemann sum. So in the next step, we're going to pick either a linear, quadratic, or cubic function. You choose the function. We will determine the area under that graph between the function and the x-axis for the given interval that you will come up with. But we need to remember these 4 identities, without which we have no tools. Okay, here's the first one. 1 plus 1 plus dot 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 plus 1. The sum from I equals 1 through n. What should that equal to? If n is 1, then I get 1. If n is 2, 1 plus 1 is 2. If n is 3, 1 plus 1 plus 1. If n is n, so the sum of from I equals 1 through n from 1 is, so if this is 3, I get 3. If this is 4, I get 4. Exactly. Exactly. That was common sense. The other 3 are not, but we can prove them if you'd like. 1 squared. I'm sorry, I need the 1 first. 1, 2, and 3, and then 1 squared, and then 1 cubed. The order is not important, but I like to do the next one. 1 plus 2 plus dot 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 plus n. This is the sum from I equals 1 through n from I. This is a formula that we used to prove them, all these 4 identities in pre-calculus. Now we don't. So this is n plus 1 divided by 2. And yes, you have to memorize these 4. Sorry. 1 squared plus 2 squared plus dot 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 plus n squared is the sum of I squared from I equals 1 through n. This is the most difficult one to remember. n plus 1, 2n plus 1 divided by 6. I'm going to copy it here because it's not clear over there. n plus 1, 2n plus 1 divided by 6. However, the cubed one is not difficult because it's the same with this, but squared. So this is the sum from I equals 1 through n from I cubed, which is the same n plus 1 over 2 and everything squared. So the second and the fourth are easy to remember. One does not have power 2, the other one does. The one in the middle for the square is a little bit more complicated to remember if you want. Okay, so now we're going to apply this. We have 15 minutes, hopefully we can determine the first function will take a while because it's a lot of work. So let's choose a function, choose an interval that you want to determine the area for. I don't want to go back to x squared because it's too simple. I want us to see a slightly more difficult example, and then we'll go back and determine exact area under x squared between 0 and 2. Yes? Eric?
Under the sigma, will the I ever equal anything besides 1?
Yes. Is the lower limit?
Yeah.
Oh, yes. You can have any integer. You can start with 0, you can start with 5, depending on the function.
Okay.
Yes, yes. The lower limit can be anything, not a negative number. Yes?
And you said the top number is the upper limit, right?
Yes.
Can you make that into the limit operator? So if you put n equals to whatever
No.
n is equal to.
No. I've never seen changing this. This is just called, by chains, it's called the upper limit, but it has nothing to do with the limit.
Okay.
Yeah, we call it the upper limit, or if you want to call it the cap limit, or I'm still using the limit. Call it the cap instead of the limit, not to get confused. It's not a limit. It's just the last number that we use the sum for. Okay, so let's make up a function. I need an interval. And we will determine the exact area using the limit of the Riemann sum, the exact area under the graph you're giving me, between the intervals you're giving me, the interval you're giving me. So now careful. If you want a simple example, you start at 0. If you want a more complicated example, you can start anywhere you want, but it will take a while. And I can show you why. Because you choose, and I'll show you. Please choose anything you want. But let's choose, because we're not going to be able to finish. Oh, and we didn't finish the problem from last time, the last one, so please remind me to go back to it. I just realized. So, please choose a function. You cannot choose any function other than linear, quadratic, or cubic. We don't have tools. If you say find the area under sine x between 0 and 1, you can't. I don't have the tools. I don't have the summation notation for sine. I only have the summation notation for linear, quadratic, and cubic. Let's say plus x plus 1. It's a very good example. We're avoiding x squared. We're avoiding x squared, which is this, which is good. Yeah, very good. Excellent. And would you like to start with 0 this time? Not next time, next time. We're not going to have, but I need to show you at least one example where we don't start at 0. So let's start at 0 for this one. And let's say that from 0 to 4? Okay, perfect. We need 3 preps before we write the limit of the Riemann sum. 3 preps. Prep number 1, delta x. Can anyone give us delta x? Say it again.
What would n be?
N. N will go to infinity.
So
N is n. We can avoid n.
So that's 4 over n.
Yes. 4 minus 0 over n. Excellent. Number 2, xi. The beginning plus I delta x. But the beginning is
The equation.
The beginning is
Oh, zero.
0. So 0 plus I delta x. Right here. The beginning plus I delta x. Very good. Finally, I need f of xi, which is f of 4i over n. How do I determine f of 4i over n? Exactly. Plug it in. Indeed. So this will be 2 times 4i over n to the third plus 4i over n plus 1. Okay, 4 to the third is 64. 64 times 2, 128. So 128 I cubed over n cubed. 128 I cubed over n cubed plus 4i over n plus 1. Now we are finally ready. Please dictate. We have all the preps that we needed, and now we're ready. So what comes after the sum? Delta x times f of xi plus delta x times f of xi plus delta x times f of xi. What is delta x?
4 over n.
Very good. Times f of xi, right here. That's why we determined it. This is f of xi. Parentheses, 128 I cubed over n cubed plus 4i over n plus 1. Remember the summation notation has two properties. I see a constant. It does not depend on I. What do I do with this constant? In front of the summation notation. Not outside of the limit because it has n in it, but definitely between the limit and the sum. Limit as n approaches infinity from 4 over n. Don't write anything. Let's try to see if we understand what happens next. We have the sum of three terms, but we have a property that we can apply. The sum of the first term plus sum of the second term plus, that's it. So let's cut back on writing a little bit. Yes, we have to put a bracket. So we have limit. I'm sorry. I just said sum and I wrote limit, sorry. So the sum from I equals 1 through n from 128 I cubed over n cubed plus the sum from I equals 1 through n from 4i over n plus the sum of 1 from I equals 1 through n. In the next step, I have to continue cleaning up these sums. Look at the first sum and say, oh, it has a constant. That constant goes outside. Look at the second sum and say, that one has a constant as well. It will go outside. You can already replace this one by what? By? That's it. That one is out. This one is already n. Perfect. So please tell me what to write next. I copy the limit. I copy 4 over n. And now please simplify the first sum. How? What goes out? Of course. Over. Very good. The sum of I cubed. This I know and I recognize. Plus, let's clean up the second sum. 4 over n times the sum of I. This I know. And plus n. Now, This gets replaced. This gets replaced. What do I replace the sum of I cubed by? N squared. N plus 1 squared over 4. What do I replace the sum of I by? Same thing without the square. N plus 1 divided by 2. Okay, for a moment, let's think. I created a limit of the Riemann sum. I took the constant in front. I said, okay, the sum of 3 terms is the sum of the first, plus the sum of the second, plus the sum of the third. I look at each individual sum, and I realize that there is a constant, 128 over n cubed, that can go outside. I look at this one, and I realize that 4 over n does not depend on I, it's a constant, it goes outside. And this one was already replaced by n. So at this step, we got rid of the summation notation. Now it's all algebra and the limit. So, limit as n approaches infinity 4 over n, 128 over n cubed, n squared, n plus 1 squared over 4, plus 4 over n plus 1 over 2, plus n. I will definitely simplify this 4 with this 128. I will definitely simplify 2 of these with 2 of these. I will simplify the 2 with the 4. I will not simplify the n because I still have an n here. So I need n in the denominator. And then we'll see what happens next. So then, these 2, these, so I have 32, these, so I have the limit as n approaches infinity 4 over n. The least common denominator is n. I have 32 to distribute to n plus 1 squared. So 32, n squared plus 2n plus 1. I have 2n to distribute to n plus 1, 2n squared plus 2n. And I have to multiply this by n because it has the denominator 1. So 32 I distributed in there, not yet, but I wrote n squared plus 2n plus 1. The 2n has to be distributed to n plus 1, and this one needs to be multiplied by n because it's n squared over n. Questions? Okay, I distribute and combine like terms, and it's done. So limit n approaches infinity. Now it's n squared. 4, 32 n squared plus 64n plus 32 plus 3n squared plus 2n. Finally, limit n approaches infinity 4. I get 35n squared plus 66n plus 32 divided by n squared. If we remember from pre-calculus what this equals to, if we don't, we have to apply L'Hopital's rule twice. But since it's same degree over same degree, where will this go? 4 times 35.